Hi, everybody. We are back for another installment related to hypothesis testing. In the last few segments, we were working on what is called the critical value approach to hypothesis testing, where we utilized the user-specified level of significance to determine the thresholds underneath the sampling distribution that define what we meant by how far is too far when we observe a sample mean that is farther away from our hypothesized population mean under the null. The p-value approach is a slightly different perspective on running the same type of hypothesis test, except it doesn't really require you to specify a level of significance up front, an ad hoc user specification, which is kind of nice. A lot of software packages will report p-values associated with running hypothesis testing. And if you know the p-value, it's very easy to just compare that to an arbitrary level of significance and understand the strength to which your evidence is conveying whether or not you should be rejecting that null hypothesis. So the p-value, the way we're going to think about this here is the probability of obtaining a test statistic that is more extreme than the one we've observed from our sample. Okay, so when we calculate our sample and we convert that into either a z or a t statistic, okay, the p-value is the probability of observing something more extreme than your z or t statistic here. It's also referred to as the observed level of significance in the test. And it also happens to be the smallest value of significance for which the null hypothesis can be rejected. It is the smallest value of alpha for which we can reject the null hypothesis. So let's get right into the p-value approach to testing here. So what we're going to do is we're going to convert our sample statistic into a test statistic, and then we're going to obtain the p-value by either using a table, right, standard normal table or the t-table, or most likely a software package. We'll see when we get into regression analysis, the software packages report these p-values pretty fluidly, and it's very, very easy to interpret the results of the hypothesis test without necessarily needing to go through the entire process within the critical value approach framework. So once we have the p-value, we're going to compare our p-value to alpha. And if the p-value is greater or equal to alpha, then we are not able to reject the null hypothesis. Remember, the p-value is defined as the smallest level of significance for which we can reject the null hypothesis. So if the p-value is smaller than alpha, then we're going to go ahead and be able to reject the null. So this is our decision rule utilizing the p-value approach. So let's go ahead and take a look back on an example that we had gone through in one of the earlier hypothesis testing videos when we had a situation where we were dealing with a scenario where we knew what the population standard deviation was, and we could just apply the z-table here. So we're going to do that just to make it accessible for us to manually find this p-value without a software package. But recall the situation that in an effort to get a loan, a clothing retailer has made the claim that the average daily sales at the store exceeds $7,500, and that's what she wanted to show here. And the question is, how likely is it to see a sample mean, and in this problem, the sample mean was $7,900, if the actual mean under the null hypothesis is $7,500. And I want to be careful here with this word true mean. What we mean here is the mean that we're assuming to be true under the null hypothesis. Remember, our approach is essentially a proof by contradiction, where we are assuming that the null hypothesis is true, and then we are using our sample evidence to try to refute that. Okay, so in the problem we had visited earlier, these were the parameters that we were given. We had a sample size of 24. We had a population standard deviation of 1,500. We had an alpha level of significance of 10%, and the z-value threshold for the one-sided test at a 10% level of significance was 1.28. Remember, this was a right-tailed test. We were trying to show that we had sufficiently high enough sales where we could refute that claim that the mean was actually 7,500 or lower. Okay, so the null hypothesis here again was that the mean sales were less than or equal to 7,500, and we were trying to show evidence against that. We were trying to show evidence that suggests that the alternative hypothesis here is maybe more valid, easily supportable with the data, in that our sales are actually much higher. Okay, so the approach we had taken before under the critical value specification is we use this level of significance to define this particular threshold value of Z. Okay. Now, the critical value approach required a specific Z threshold be calculated, and then we would compare our test statistic relative to that particular value. Now, our test statistic here in this problem is a Z value of 1.31 after we convert our sample mean using that Z transformation. So we could see here for sure that if we wanted to know the probability that Z was between 0 and 1.31, we could calculate that using that standard normal table. Now, that's not the p-value that we are interested in this framework, and I'll come back to that in just a second here. So in order to calculate the p-value, what we're actually going to find here is the probability that we would observe a value more extreme than 1.31. That is the p-value. Okay, so you'll notice that's different than alpha, right? Alpha is the probability we observe a value more extreme than the critical value, which defines the rejection region. Okay, but the p-value is us looking at the probability of seeing something more extreme than 1.31. And we're in a position here to use the standard normal table to think about this, because remember, the standard normal table, that is going to give us the probability of observing something between 0 and 1.31. Okay, but that's not the p-value. The p-value is going to be the 0.5 minus this probability, right? This is the probability Z is between 0 and 1.31, but the p-value is the probability of us observing something more extreme than that, which is really the probability of observing something greater than 1.31. So hopefully you have your standard normal table handy to access, because we're going to go ahead and need to retrieve that particular value to give us the area to the left of 1.31 in between 0 and a z-score of 1.31. And then we'll be able to subtract that from 0.5 to actually calculate the area to the right of our z value of 1.31. Now you'll notice in this diagram, we can see here clearly we're in the rejection region. We saw this last time we had run with this example using that critical value approach. But now we're going to calculate the p-value, and we'll see that it's very easy to note how you can compare the p-value to the level of alpha and conclude that you must be in that rejection region as well. So in order to do this, we're going to have to figure out the area to the left of our test statistic, that z-value of 1.31. We're going to figure out what that area looks like, okay, by using our standard normal table, and then we'll be able to take 0.5 and subtract this area out of 0.5 to leave us with the probability in the upper tail. So I want to be very, very clear about this. The p-value we are looking for here is in this red region that I'm kind of shading in right now. Okay, that is the p-value that we are looking for. Okay, note it does not include a little bit of this pink region. That includes the alpha region, the rejection region for the alpha probability, which is user specified. The p-value is not user specified. Okay, the p-value is a function of your sample statistic. That sample statistic here being that value 1.31. That is our sample statistic. Okay, so what we want to do now is go to our standard normal table. We're going to look up 1.31 in the standard normal table here. And when we do that, and we should be able to see here that the value 1.3, so here is the row we want to be at, 1.3. Okay, and we want to go to this column for 0.1. That's 1.31. And you'll note that the probability there between 0 and the z value of 1.31 is 0.4049. Okay, so let's go ahead and jump back to our problem, we now know what the area to the left of 1.31 is, in between 0 and 1.31. But the p-value that we actually want is not that area. It's the area to the right of 1.31 in that upper tail that I had highlighted before. Let me just draw that again in there so we can see that clearly here. That area, again, our p-value is defined in this region here. Okay, everything to the right of 1.31. That is the p-value in this example. Okay, so to calculate this p-value, we're going to take 0.5, we're going to subtract out 0.4049, and that gives us a p-value in that upper tail there corresponding to about 9.51%. Now you'll notice that p-value is smaller than alpha, right? The area that I've kind of shaded in red here, that is a smaller area than the pink region, which was defined by that alpha level of 10%. So in order to make our conclusion and to apply our decision rule here, we're going to go ahead and compare that p-value with alpha. Again, if p is greater than or equal to alpha, we're not able to reject the null hypothesis, because that means we're not in the rejection region. But if p is smaller than alpha, then we can go ahead and reject the null hypothesis, because that must mean we are in the rejection region, as we saw in the previous diagram. So the conclusion here is, because the p-value of 9.51% is smaller than our significance level of 10%, we are able to reject that null hypothesis, and we can conclude here that there is, in some sense, a 9.51% chance of observing a test statistic that is more extreme than our test statistic of 1.31. Okay, so in terms of statistical significance, what type of p-value suggests we have very strong evidence here? The answer is smaller p-values. Okay, the smaller the p-value is, the more likely we are going to be to reject the null hypothesis. Okay, the smaller the p-value is, the stronger the evidence is. The p-value and the strength of the evidence, they are inversely related to each other. Okay, now, in terms of interpreting the p-value, if that p-value is, bigger than 10%, right? Our standard levels of significance I've shown here in this diagram, and let me go ahead and clear that drawing. But our standard levels of significance here are 10%, 5%, and 1% that practitioners typically use. So if a p-value is larger than 10%, that means we would not be able to reject the null hypothesis even at a 10% level of type 1 error that we're willing to accept. Okay, so if the p-value is relatively big, how big? Bigger than 10%, I would not be able to reject the null hypothesis in any three of those cases of using alpha at 0.01, alpha at 0.05, or alpha at 10%. But if the p-value falls in between 5% and 10%, what does that mean? Well, that means I would be able to reject the null hypothesis at 10%, but I would not be able to reject it at a significance level of 5%. So this is some weaker evidence, but it is significant at the 10% level. If we had a p-value that falls in between 1% and 5%, that means we would be able to reject the null hypothesis at both the 10% and 5% levels of significance, but we would not be able to reject it at the 1% level yet. The evidence is not quite that strong to reject it at the 1% level, but it is definitely stronger than if it was falling in between 5% and 10%. Okay, overwhelming statistical evidence is when your p-value is very close to 0, right? Smaller than even 1%. If the p-value falls in between 0 and 1%, that means you can reject the null hypothesis at all of those three standard levels of alpha. Okay, so the p-value is nice because I don't need to think at first what's the level of alpha that defines the cutoff region. Okay, the p-value can be reported, and then after the fact, the user can decide on how good the strength of the evidence is relative to those different values of significance. So again, the critical value approach, right? If the researcher decides to reject the null hypothesis at a 5% level, okay, well, if we change that significance level, we would have to run the whole test over again to check, because we know the critical value thresholds change if we were to change the level of significance. And again, we have to ask ourselves, how close is that test statistic to that critical value? Will we still be able to reject it if it was a 1% level of significance? And again, we would need to run the test again. However, if we were just given the p-value, it doesn't matter if the significance level was 5% or 1%. We could immediately compare that p-value to both. Okay, if a researcher decides to reject the null hypothesis at an alpha of 5%, okay, with a smaller p-value of 4.99%, then we wouldn't really need additional evidence to determine the strength of the test results here. Okay, we know we definitely would not be able to reject if alpha was 0.01 without needing to go to our table and figure out a new critical value threshold for that. Okay, so again, in this problem here, referring to the daily sales example, would we reject a null hypothesis if alpha was at 5% instead of 10%? And the answer here again relies on us comparing that p-value to the level of alpha. So remember what our p-value was. Okay, our p-value was the area to the right of 1.31. So again, I can fill that in here. I could draw that in here. Okay, our p-value is this entire blue region. Okay, including that portion of the tail there. Okay, that is the p-value. Okay, 9.51%. Okay, note, now at a smaller level of alpha, at a lower level of significance here. Okay, we're using a slightly more sensitive test, if you will, right? Under a 5% level of significance, we need the evidence to be even stronger, to be even farther away from that mean under the null. And in this case, we can compare our p-value to alpha, and we see that we cannot reject the null hypothesis anymore because the p-value is larger than alpha. So the answer here is no. At a 5% level of significance, our test statistic does not provide us strong enough evidence to reject the null hypothesis. So let's go ahead and take a look at another example here. So in this problem, Vodafone believes that the Nigerian market has much potential for growth. Due to recent competition, the average monthly revenue earned per customer in Nigeria has been falling steadily since 2006 and is currently at $11. Vodafone wants to test the validity of this claim at a 5% level of significance. And in a random sample of 65 observations, the average monthly revenue is $12 with a standard deviation of 2.75. Okay, so they want to test this claim here. And again, let me clear that picture. Apologies there. They want to test this claim that the current level of sales is currently at 11. Okay, and our sample evidence here says, hey, it's actually a little bit higher, but there is some error, right? There is some standard deviation. Okay, so that being the case, first thing we have to do is figure out our null and our alternative hypothesis. And again, the null hypothesis here is what we're trying to disprove. And it looks like our evidence says $12 revenue is different than 11. Okay, so the forms of our null hypothesis. Remember, null hypothesis always has to include some form of the equal sign. And in this case, all of them do. So that doesn't really help us eliminate answer choices here. But we're actually dealing with a two-sided test in this case. Okay, the claim is that the revenues status quo are at 11, but our evidence suggests that it is different, which means we are testing the null hypothesis in B against the alternative that mu is not equal to 11. So we're using a two-tailed test here. Okay, at a significance level of 5%, and hopefully you remember that's a standard significance level for a two-tailed test. And that would correspond to the same thresholds as a 95% confidence interval, okay, where you have 2.5% probability left in each tail. And if we were using the critical value approach, okay, we could find that z-value threshold. It's a very commonly used z-value threshold, which is 1.96 standard errors away from the center of the distribution under the null. Now, what is the decision rule if we're going to use the p-value approach in this next question? Well, remember, the p-value approach says we are able to reject the null hypothesis provided the p-value is very small. How small? It needs to be smaller than that level of significance alpha in order to reject. So the correct answer here is choice A. We need the p-value to be sufficiently small to reject the null hypothesis. Now, next step in the process in getting that p-value is computing our test statistic. Okay, and again, we're going to compute that test statistic here. And we're abusing a little bit, right? Given that the standard deviation from the sample is given here, but we're going to go ahead and use the z-value anyway, just because we have that table accessible. And it's technically be more correct if we use the t statistic here. But we're going to go ahead and just use the z statistic instead, so we can use our standard normal table to think about the idea of computing the p-value in this instance. So our test statistic, if you were to compute that for this example, involves us again demeaning x bar of 12. We're going to subtract out 11, divide by the standard deviation over the square root of n, which will give us a z-value of 2.93. Okay, so this says our test statistic is about 3 standard deviations to the right of the mean, okay, which is pretty extreme. But in order to know if the evidence is good enough, we're going to have to compute the p-value and compare that to our level of significance alpha here. All right, so let's go ahead and do that. Okay. So the p-value, okay, we have our two-tailed test, and just for reference, I've put in our critical value thresholds here, but we don't actually need those if you're utilizing the p-value approach. So in order to get the p-value, we need to know what is the probability of observing something more extreme than 2.93. And in order to figure that out, it's going to help us to use our standard normal table to find the probability that 0 is in between 2.93. So I'll give you a moment to go ahead and do that. Okay, if you need to pause the video, please go ahead. And if we were to look at the table value associated with a z-score of 2.93, we would see that comes out to 0.4983. And if we subtract that from 0.5, that will give us our p-value. Okay, and you'll note here we did something important. Okay, it says here this is the p-value divided by 2. And the reason why we have to divide it by 2 is because we're using a two-tailed test. So that probability of observing something more extreme than our test statistic in this case, that is the area just in the right part of this tail here, this blue region, just the area of the right part of that tail. But remember, we also could have had evidence show up in the left part of the tail as well for us to invalidate the null hypothesis. So if you're doing a two-tailed test and you compute that probability in the upper tail, you're going to have to double that to actually get the p-value in order to compare it to the level of significance. Or conversely, you could cut the level of significance in half to 2.5%, and you can compare these two numbers directly. I can compare 2.5%, 2.0017. That's me comparing half of the significance level to half of the p-value, right? So as long as half of the p-value is smaller than half the significance level, we can reject. Or what can you do? Well, you can double the p-value, or sorry, double that probability we just calculated in that blue region there. And when we do that, we get a p-value in both tails of 0.0034. Note that that is definitely smaller than our significance level of 5% here. Okay, so that is the p-value for this problem. We looked at that little blue region that I had shaded in. Okay, the probability of observing something farther to the right than 2.93, and then we had to double it because it was a two-tailed test here. All right, so given this sample, is there statistically significant evidence to suggest that the claim is true? Okay, and the answer here is no, their claim is not true. Okay, the sample data was far enough away because it gave us a smaller p-value than we had under the, than we had relative to our level of significance alpha. Okay, now there is a very important relationship, and I know I've alluded to this a few times already, between a two-sided hypothesis test and a confidence interval. Okay, and I want to just mention this briefly and then we'll wrap up. But suppose we have created a 95% confidence interval for mu, with the result being 10 to 15. Okay, so there's our confidence interval. Question is, what decision will we make if we test the null hypothesis that mu equals 16 versus the alternative hypothesis that mu does not at an alpha level of 5% here? Okay, so this is what the rejection region would look like, and the non-rejection rather would look like for this situation. Okay, so what we've done here is we've created a confidence interval, and you'll notice that confidence interval is not centered at 16. We're actually using the sample distribution for the confidence interval here. So what is it centered at? Well, it's centered right between 10 and 15. So it's actually centered at a value of 12.5. Okay, that is the center of this distribution. And the way we can think about the relationship between the two-sided hypothesis test, the two-tailed test, and the confidence interval is if the hypothesized value of the mean under the null, which was 16 here, okay, if that falls, sorry, let me redraw that. So our hypothesized value of the null, 16, if that falls outside of our confidence interval relative to our sample mean, then that is equivalent to us being able to reject the null hypothesis of a two-tailed test that uses a 5% level of significance here. Okay, so in this situation, we would be able to reject the null in favor of the alternative, since the value under the null is not in the confidence interval given to us that we've constructed around our sample mean. So the conclusion is we would reject the null hypothesis in favor of the alternative at that 5% level of significance. Okay, so the interpretation again is at that level of significance. There is there is enough evidence to reject the null hypothesis in favor of the alternative hypothesis if the population mean does not equal 16. So this is the important link between the confidence interval and the two-tailed test. Okay, and the way the decision rules are related are as follows. We do not reject the null hypothesis if the hypothesized value of the mean under the null is contained in the confidence interval, where the confidence interval is built around the sample mean. Okay, the confidence interval is built around the sample mean. So that is where I would like to leave off. That is the summary of the p-value approach to hypothesis testing. A little bit easier to use because you don't have to specify a level of alpha. You just look at how small is p, and you can know already what levels of significance your results would be able to reject that null hypothesis at. So hope you enjoyed. Stay tuned.